All right, so I welcome you to this video on Introduction to Exponential and Logarithmic Function. What we see on the screen is a little task for us to talk about it. So for now, let's just pay attention to the following. We have to sketch the graph of this function here. So that's the exponential function. And then the graph of this type of function, which is a logarithmic function. So that's the objective here already. So let's begin with the following. I have to change the pen slightly. The table of value for exponential function is right here. And we have randomly selected values of x. So this is the domain values. -2 will give you 1/9. And how is that? So since the formula says y is equal to 3 to exponent x, so 3 to -2, if you remember the negative exponent rule, you will get 1/3 squared, which in effect gives you 1/9. So this is why for -1, you get 1/3. So supposedly points are somewhere here on the graph. So -2 for -1 is 1/3. For 0 you have 1. So this is called the y-intercept because you're cutting through the y-axis. So y-axis here, this is the x-axis. When x is equal to 1, then you would have 3. So for this value of 1, you have 3 somewhere here. And the last point, when x is equal to 2, y is equal to 9, we don't have the room on our scale, but you can sort of imagine. So those are the points that would define that exponential curve. Now, the inverse function. The inverse function graphically is always obtained when you find a symmetry and the line y is equal to x. So these two graphs are symmetrical and this line y is equal to x. What happens algebraically when you have a point, let's say with coordinates x and y, the inverse point will be found when you switch the values around. Okay, so that's mathematical approach to defining inverse function. So logarithmic function is defined as inverse function to exponential function and vice versa. So this graph here, right at the bottom, the one with points here, the purple one, is called logarithmic function. Now, start with point where x is equal to 0. So what happens? That symbol, y is equal to logarithm to base 3, and the proposition is how much is y when x is equal to 0? So you plug in 0 for x, and you're looking for the value of y. And since logarithm is the exponent, because to resolve for that, we will find 3, if possible. 3 to what exponent is ever equal to 0. And we know from our experience, and we also understand that if you ever try to plug in any value for y, you can never ever get 0. So this is why the value of x when x is equal to 0 is undefined for logarithmic function. Okay, so moving down, if x is equal to 1, log 3 of 1 is equal to 0. And why is that? If x is equal to 1, so I have to find log to base 3 of 1 is equal to what value? So I'm thinking of 3 to what exponent gives me 1. And the answer is 0. So this is why when x is equal to 1, y is 0. When x is equal to 3, so let's erase that. When x is equal to 3, so the challenge is find y. So this is the point that we're looking for. So you're thinking of finding solution to logarithm to base 3 of 3 is equal to what possible value? So thinking 3 to what exponent gives me 3? And the answer is 1. So there you go. So when x is equal to 3, the y value is 1. So let's say this is that point. This is the x-intercept when x is equal to 1. And when x is equal to 9, we have the y value is equal to 2. And then when x is equal to 10, this is the approximated value. You cannot expect always a definite finite number working with logarithms. Therefore, in between whole numbers that we are able to find using this particular chart, we also have found that there are other real solutions to this equation. So whenever you have exponential function to base b with exponent x, logarithm to base b of x is called the inverse function. So, and vice versa, if I start with log function, the inverse is exponential function. So that works both ways. And graphically, we see the symmetry between two graphs in that line y is equal to x. Okay, now on this screen we have three different graphs, exponential equations. And the challenge is here to match each graph with the equation. So a to the power of x, then 6 to the power of x, 4 to the power of x. So by just logical, critical thinking, you would say that if I have a bigger base and I put to the same exponent, I expect a larger result than smaller base to the same exponent. Just by inspection, 8 squared versus 6 squared versus 4 squared. Where do you get the largest value? Right here. So this is the fastest growth on the graph. So they all share, interesting enough, all exponential graphs will pass through that y-intercept 0, 1. Okay, so they all share that. As you start introducing greater values of x for that base, the bigger the base, the faster is the growth. So this is graph which corresponds to number 1. The second is number 2. And the slowest, relatively slowest graph will be 4 to the power of x. So generally, they all have the same behavior. They do increase on the entire domain. They all pass to the same y-intercept. And that horizontal line here will be called horizontal asymptote. So those are the key feature of exponential graph when the base is greater than 1. Now, by the same analogy, what will be the corresponding graph of logarithmic function? So let's think for a second. This is the same point for all three graphs. 0, 1, the x-intercept. Oops, it's not 0, 1, it's 1, 0. Sorry for, okay, for that. Boom, 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 quickly. Okay, so this is x is 1, y is 0. Just remember the 0.01 now an inverse function became 1, 0. We have switched values x with y. Okay, so this is y. From y-intercept, we have the x-intercept. Remember we said that see the graph from previous example, the bigger the base, the faster is the growth. That was the steep graph with the base 8 to the power of x. So when you do the line of symmetry, you expect to find a graph closer to x-axis. So the larger the base, the flatter will be the logarithmic function. So this is C corresponds to number 1. Then B, base 6 will be number 2. And A corresponds to base 4. Just by the feature of symmetry. A to the power of x would correspond to logarithm to base 8 of x. So for exponential function, the bigger the base, the faster is the growth. For logarithmic function, the bigger is the base, the slower is the growth for now. Okay. If possible, graph a function, logarithmic function, where the base is greater than 1. Just recall the previous examples. We had logarithm to base 8, or 6, or 4. They all behave in the same fashion. Same x-intercept at 1 and 0, always increasing. And the key here is to observe that this vertical line not supposed to be ever intersected, although it shows here, but please do understand that that never actually takes place. It is impossible. Recall the table of values. We were supposed to find logarithm to base 3 when x was 0, and there was no answer to that. It does not exist. So therefore, they all have to be bordered by this vertical line. So no graph, logarithmic graph, can ever run into y-axis. So this is the same property for all logarithmic functions when the base of the logarithm is greater than 1. Excellent. Okay, now the base has changed. It became a value between 0 and 1. For example, logarithm to base 1 over 3 of x. If you can relate to the graph 1/3 exponential function to the power of x, 1/3 to the power of x will be a decreasing type of function that would look somehow like this. So 1/3 will be decreasing function, and then think of a line of symmetry. A line of symmetry that splits. I'm going to create right here this line of symmetry that splits these two graphs. So this is the point where you keep the same coordinates for both, okay? Because they are intersecting right here. So this branch is corresponding to that. So the symmetry is right here. And this part of the graph is symmetrical in the line with this portion of the graph. So when the base is less than 1 for exponential function, the graph is decreasing, and the logarithmic graph also behaves in the same fashion. So all logarithmic functions when the base is between 0 and 1 will have the same characteristics. The vertical line is the y-axis, is the vertical asymptote, so the contact should never occur, and the graph is decreasing always, and the x-intercept is constant for all logarithmic function 1, 0. Okay, and now the challenge is to find possible graph when the base is equal to 1. Recall exponential function. 1 to exponent x is always equal to 1. So you would have a graph that looks like that. A horizontal line will be 1 to the power of x. So no matter what value of x you will select, the result for y will be always 1, continuously 1. So the inverse function, so from horizontal, you will flip into vertical line if you were to find the graph of logarithm of x to the base 1. And how is that? 1 to what exponent will give me whatever the exponent is, you always get 1. So any value of y, you plug in right here, anything, you always get 1. So x is always 1 for any value of 1. So this is the graph of logarithmic function. This would be the graph if that function existed. It's not a function. This relation, because it's a vertical line, when the base was 1. So in general, just recall, logarithmic functions do exist when the base is either greater than 1 or in between 1 and 0. The base can never be equal to 0, can never be negative. So those are the two possibilities that we have when working with logarithmic graphs. I hope you have enjoyed this video and that served you the purpose of learning the fundamental feature of exponential and logarithmic functions. There will be more video coming up, so stay tuned. Talk to you later. Bye for now.